Hi guys, so in this lecture, I want to explain the most basic or the most structural part of the calculus you guys are going to learn this quarter, and that is the fundamental theorem of calculus. Now, the idea of fundamental theorem of calculus is what leads to what you guys learn in math 1A at the end when we're talking about the antiderivative. So somehow it connects the idea of integrals, which was the area, and related to area, and the geometry that I showed you guys. It's going to connect that to calculating antiderivatives in the case of definite integrals. Again, if you have questions what definite integral means, definite integral is when you have fixed bounds for your integral, and it corresponds to the net change of the function. So that's the one that we talked about, and that's the same one that we had the limit of the Riemann sum. I don't know if you guys remember. So that's the definite. Whenever I say definite integral, I mean those are the, it's a bound. There are bounds for the integral, finite bounds for the integral, and so forth. And we talked about properties of that in the last lecture and so forth. So you should kind of review that before probably this part. Now I'm gonna first define a function before we get into this. So I'm gonna just define a function. I'm gonna say suppose that you have an f of x, and this is just a normal function that's, you can at this point you can say it's positive, it doesn't have to be. It's just a nice continuous function. Even continuity may not be required at this point, but let's just say you have a nice continuous function that you have for your integration. Remember, if it was in piecewise continuous, I could still calculate the area. But for specific thing I'm going to say now, I'm going to assume that f is continuous. I'm going to assume that my picture looks like it's positive and so forth. But again, so, and of course, I start from some a. And suppose that I define a function g, where the g of x corresponds to the area bounded under f and x-axis, and it's from a to x. Okay, so as x increases, that area in this picture gets bigger. Of course, if the function had negative parts to it, then that would not be the case. But in this picture, as x increases, the g of x would increase. So g of x is this, that area. Okay, I hope you can visualize that. So it's kind of like, so as I keep moving to the maybe right, then the g of that new x, if this is x1, that the g of x2, for example, would be that part. G of x3 would be that, the portion up to that next piece. A quick observation, I guess you all agree that g of a would be integral from a to a of f of x, which is 0. So that's like if it was here. But anyways, in general, I define g of x again to be integral from a to x of. Now, the problem here is I cannot use x both as my bound and as argument of my function. So I'm just going to use a dummy variable t. It's called integration variable. It doesn't cause any problem to use a different letter. In fact, this is the same thing as saying f of p dp. It's the same thing as saying f of star d star. It doesn't make a difference. It's just a dummy integration variable. That's all it is. Okay. So I hope you understand what that g is. So the question here is, or the first part of the fundamental theorem calculus makes some claims on that g. And fundamental theorem calculus part 1 says that, and again in a simple form, says that if f is a continuous function over AB, then function g defined by the same definition that I say, gx equal to a to x f of t dt. Again, x values here are between a and b inclusive, is also continuous. That's why we expected, we started by assuming continuity of f. Again, that's a technicality we can talk about a little bit later on AB. And here's the important part. It's differentiable on the open interval AB. We don't discuss the endpoint differentiability there on open interval AB. Furthermore, its derivative is f of x. Fundamental theorem calculus part 1. So before I prove it for you, let me first actually go ahead and give you some examples of how we could apply this. So for example, if somebody says, suppose f of x is x squared plus 5. Okay, and let's say over 1, 7. It doesn't matter what number, as long as the function is continuous over that, we're all fine. If I define g of x to be integral from 1 to x of t squared plus 5 dt, and again, because I'm using x as my variable, then t becomes my integration variable, my dummy variable. Then if I calculate derivative with respect to x of g of x, it literally becomes just f of x, which is x squared plus 5. So the function could be very complicated. Suppose if I say integral from 5 to x of natural log of 3t squared plus 5t minus 1 over t dt. Very not friendly function. And somebody says, hey, can you tell me what is derivative of this with respect to x? I use my fundamental theorem calculus knowledge. I'm like, well, so this is my fixed bound down here. This is my variable bound. I'm taking derivative with respect to that variable. Fundamental theorem calculus says the derivative integral becomes just a function inside. They cancel each other out. So in a way, all I'm going to be left with what's in the integrand, but instead of t, I just put x. Without mentioning it, I did check the continuity of my function, and my function is continuous on the interval 5 to whatever x is. Things can get a little bit tricky. For example, somebody could say, oh, how about d dx of x to 2 sine x t squared minus 1 dt. It's a sine function. Obviously, I expect continuity, so no problem. But do you notice between that and the form of fundamental theorem calculus, the function that we define? In that function, the fixed bound is at the bottom, the variable bound is at the top. Fixed bound is at the bottom, variable bound is at the top. So here, variable bound is at the bottom, fixed bound is at the top, but still I'm taking derivative with respect to that variable bound. All right, I'm going to use one of properties of integrals that I mentioned last time, which was integral from a to b of f of x dx is negative integral of b to a of f of x dx. So I'm going to switch the bounds and change the sign. And now all it means is integral and derivative cancel out. And I just plug in x for where there is t. Okay. So that's how we handle something like this. But what if my bound is not just the variable? What if it's a function of the variable? How do I handle that? Well, if you have cases like that, then you can do something, again, the chain rule you learn from 1a. So let's just give an example. I have d dx of, say, 5 to x squared, not x, but x squared. And let's just have like say tangent of, let's just stick to a more simpler function for now. 3t squared plus 5t minus 1 dt. I don't want to bring in any trig functions or anything more complicated. Let's just work with polynomials for this example. So what I'm going to do is what you would do probably in any algebra class or any math class. If you see something that it doesn't look friendly, but you know the process for a simpler form of that, usually what we do is we introduce a substitution. We say, okay, let u be x squared. There's nothing wrong with that. You can always do that. So you have d dx of 5 to u 3t squared plus 5t minus 1 dt. Not just instead of u, instead of x squared, I put u. No problem. You can always do that. But the problem is now the fundamental theorem calculus doesn't apply. Because for fundamental theorem calculus, I need to have the bound to is the u, the derivative has to be with respect to u as well. So the bound is u, but the derivative would have to be with respect to u. But here my derivative is with respect to x. So what we do is we're going to apply chain rule. I want to have d du here, but I have is a d dx. So I'm going to write it as d u dx times d du. Now du dx and d du by chain rule using this Leibniz notation, we will see that the du's would quote unquote cancel and you get d dx. Right? So d dx is what I had, but I want to have d du. So I write the d du and I multiply by du dx to the end result after chain rule would be d dx. Now I have a very nice fundamental theorem calculus form, and I have to calculate du dx, but du dx is not hard. It's just 2x. Just take the derivative of u with respect to x, you get 2x. So now I have 2x for the first part, and the rest is fundamental theorem calculus, which is 3u squared plus 5u minus 1. You put u everywhere there is a t. But u is not your variable, x was your variable. So you have 2x, 3u was x squared plus 5x squared minus 1. Ta-da. So that's how you handle. Let's do one more. Let's do one more just so I can show you how. Let's say d dx of, let me just do something a little more interesting. Sine x to 2 t cubed minus 5 dt. Okay. So first things first, I have to make it in the form of a fundamental theorem calculus, which means I have to switch the integral, the bounds of the integral. So there's a negative that creates there. Then I have to do a u sub. So I let u be sine x. Of course, I know later I'm going to need du dx, which is cosine x. So I have the minus from the problem. I change d dx to du dx times d du. That chain rule process gives me the dx. And then I have 2 to u t cubed minus 5 dt. Du dx we just calculate is cosine x. d du and u is just an integral from 2 to u of the function. The derivative integral cancel out. You just get u cubed minus 5. And u cubed in this case would be sine cube x minus 5. So that's how you apply fundamental theorem calculus part 1 in canceling integrals and derivatives, but it's just very specific on the form, though. It's not just. Let me do something more, I guess, interesting. Suppose somebody asked to do dx of, let's just say sine x to cosine x, just of t squared plus 5t dt. Okay, so if I'm calculating this, what I'm going to do is I'm going to first split my integrals to two integrals. Remember, that was one of the properties of integration. And I need to do that because I need a fixed bound. Remember, my fundamental theorem calculus requires a fixed bound. So I'm going to break it into d dx of, and it doesn't matter where you split. Of course, you have to worry about the continuity of the function and such, but other than that, there is nothing else that matters here. So I'm going to split it to, say, 0 to cosine x, t squared plus 5t dt, plus sine x to 0. As the combination, these two add up to the same thing here. Then I have d dx of 0 to cosine x, t squared plus 5t dt. And then here, I'm going to switch the bounds of the integral. Once again, for each of those, I'm going to apply the process I taught you. So here I'm going to let u be cosine x, du is negative sine, du dx is negative sine x. So you get du dx ddu 0u t squared plus 5t dt minus the, let's call this now v, d v dx v of 0v t squared plus 5t dt. So here I do substitution sine equal to v. On the other one, I do substitution cosine equal to u. So I'm going to have negative sine x for du dx. This part is fundamental theorem calculus. Once again, cosine x for dv dx, fundamental theorem calculus. And then I have to replace u with cosine and v with sine. And in an unsimplified form, this is good. If you want to simplify it, it just combines these two. And that will be your final answer. So basically, this is how they want you to do some of the homework problem I assigned for you to apply fundamental theorem calculus part 1. The proof of fundamental theorem calculus is in the book. It's on page 394 of Stewart's 8th edition book. But I will still make a video for that one as well. So you guys who are interested in, you're not responsible for the proof, but for those of you who are interested in knowing how it works or the explanation of it, I can explain that in a separate video. Okay, we have a second part of fundamental theorem calculus, which also is going to be on another video. So this would get you through the problems related to fundamental theorem calculus part 1. Thank you.